This video is going to continue looking at upper and lower sums, and this time we want to look at the upper sum. So now we want to look at calculating the upper sum, so our area is going to be a little bit greater than the actual area. So we want to draw our rectangles going up and above the curve. And recall the last example in the previous video we looked at here, the function negative x squared plus 5. Using 5 rectangles, we were able to estimate the area under the curve by using our lower sums and drawing the rectangles below the curve. And I really want to emphasize here, when we did this, we were looking at, on this case, we were looking at the right endpoints. So if you look at each of our rectangles here, we were using the right endpoints. Notice we have 2/5, 4/5, 6/5, 8/5, and 2. Whereas if you were using the left endpoints, we would use starting over here at 0. So be careful. Notice here we have 2/5, 4/5, 6/5, 8/5, and 2. So that's 1, 2, 3, 4, 5 rectangles. Don't fall into the trap of using the 0, because if you use 0, you're looking at calculating 6 rectangles instead of 5. Now, it's not always going to be the case that the right endpoint is going to be the lower sums, because it really depends on the shape of your curve. If your curve is going the other direction, this one's being curved down. If the curve was going up, then maybe your endpoints would be different. So for lower sums, you're not always going to use the right endpoint. Sometimes the left endpoint would calculate the lower sum. Okay, it all depends on the curve, which way it's sloping, and where your rectangle is going to fall beneath the curve. Okay, so I don't want you to always assume, for this example, the lower sum happens to be using the right endpoint. Now, if we take the exact same problem, same function, now we want to look at calculating the upper sums. And we're still going to use our 5 rectangles. We're still looking at the interval from 0 to 2. So clearly, if we want to calculate the width, then we would take the total distance of our interval, which is 2 minus 0, and divide by 5. So we have a width again of 2/5. So that's not going to change. We would still have our 2/5, 4/5, 6/5, 8/5, and 10/5, which would be 2. The part that's going to be different now is, because we're looking at the upper sum, we want our rectangles to go above. So here, I'm going to look at drawing the left endpoint, which the first one, if we start at 0, notice when I go up here, I'm going to hit the point here, which is right at 5, and I'm going to draw my rectangle over and down to the 2/5. So this first one just barely is slightly right at, or just a little bit above the graph. And then we're going to draw our next rectangle, and we're going to pick this point here and go over and down to the 4/5, and then we'll pick our next point, go over and down, over and down. So if you notice, once again, we still have 1, 2, 3, 4, 5 rectangles, and we're still using the same 0 to 2/5 and 2/5 to 4/5, and from 4/5 to 6/5, and from 6/5 to 8/5, and from 8/5 to 2. Now, the only part that's going to be different now is because we're looking at, we want to find the points now that touch the graph. Now, let me go back up to our previous example we looked at Notice our endpoints here that actually touch the graph on the top for the rectangle. We have the blue dot, the red, the green, the purple, and orange. Notice how the right top corner of the rectangle is touching the graph, because that point will give us the length L1, L2, L3, L4, L5 of each rectangle by knowing the Y value of the graph. So down here, we want to do exactly the same thing, but notice now it's our left endpoint that we're going to use. So for this one, here's my point right here at 5 on the y-axis. This is going to be L1. And then we would have our next one here. This point for the 2/5 would be L2. And then this point here would be L3. And then we have L4. And this point is L5. So there again we have the 5 lengths of our rectangle, and of course the width is always going to be 2/5. So when we go to calculate the area, we know that 2/5 is going to be multiplied by each one of them, and remember before we simply factored out the 2/5, so we would really just end up with L1 plus L2 plus L3 plus L4 plus L5. So just like before, we could just add up all of the lengths and multiply by 2/5. Now the question is, how do we find L1, L2, L3, L4, L5? Well, how did we do that before? We had to take each point for L1, we had to plug that into the function. So we know that we used the right endpoint here as 2/5, so we evaluated the function f at 2/5. And then for L2, we evaluated the function at 4/5. So now notice we're going to do the same thing, but where up here we were using the right endpoint, we went 2/5, 4/5, 6/5, 8/5 to 2. Notice what's going to happen now. We're going to start at 0 and then go to 2/5, then go to 4/5. So we're going to get, at 0, you're going to get this first rectangle here, and then at 2/5 we're going to get the second rectangle, and at 4/5 we're going to get the third rectangle, and at 6/5 we're going to get the length here of the fourth rectangle, and at 8/5 we're going to calculate here the length of the fifth rectangle. So here we're going to evaluate f of 0, and then we're going to have plus f of 2/5 plus f of 4/5 plus f of 6/5 plus f of 8/5. Okay, now don't make the mistake and use the 2, because notice we said 0, 2/5, 4/5, 6/5, 8/5, so that gives you 1, 2, 3, 4, 5 rectangles. That's all we need. We're talking about 5 rectangles, so there's the 5 lengths. If we were trying to use 2 again, then we're trying to calculate the length of this very last rectangle again. So be very careful. I know it's a common mistake to include each interval, but remember for this example, we were using the left endpoints up here. So when you set a problem up like this, you may want to indicate that you're only using the left endpoint. So again, you end up with 1, 2, 3, 4, 5 rectangles. And if we go through all the calculations, if you plug f of 0 in, now realize all of these numbers here that we calculated, we already calculated above 2/5, 4/5, 6/5, 8/5, right? Up here, the 2/5, the 4/5, the 6/5, the 8/5, all of these values would be the same, 4.84, 4.36, 3.56, and 2.44. Now we're going to leave off the f of 2, but we have to include the f of 0. So the only thing different here is we got to plug 0 in, and of course if you plug 0 in, that's going to be 0 plus 5. So we would have 5 plus the answers we had before, but we want to leave off the f of 2. So it's going to be 5 plus 4.84, 4.36, 3.56 plus 2.44. And notice this time we're going to come up with an area that's equal to 8.08. And for this example, realize this is going to be slightly greater than the region that we're looking for, because notice we now have this little extra space above the curve that we are calculating as part of our area. So here we had 8.08, and before we had 6.48. So we know that if we had 6.48 before, then the actual area is going to be greater than that, but it's going to be less than 8.08. So we know it's going to be somewhere in between 6.48 and 8.08. Now, can we set up, just like we did above, can we set up using our sigma notation for a formula that we could enter into the calculator? Now again, using this sigma notation is optional. You can certainly just do the calculations like we did here on the right by hand. All we had to do was do the substitution into the function and perform the calculations. Now, let's look at how we could set up using our summation. So if we want to calculate the area, once again, we know that we're going to start with I equals 1 to 5, and that's because we want to sum up 5 rectangles. And we know the width, once again, is going to be 2/5. So here's our width. And now we need to determine how will we calculate the length. Now keep in mind this is going to be a little bit different. Before we said it was going to be f of 2/5 I, because we start here, we know the width is 2/5, so we're going to increase or multiply each time to include the space for the width. So for example, if I is equal to 1, if we plug 1 in for I, we get 2/5. Well, notice this time though, we don't want to start at 2/5. We want to start at 0. So if we plug in a 1, we're going to get 2/5. Okay. If we plug in a 2, we're going to get 4/5. Plug in a 3, you get 6/5, and so on. And then a 4 is going to give you 8/5. But notice we don't want to start at the 2/5. Well, if we plug in a 1 and we get 2/5, then we want to subtract that away, so we could simply just subtract 2/5, and that would cause us to start then at 0. So let's see if that'll work. If we plug a 1 in for I, we get 2/5 minus 2/5, which gives us our 0. And then when we plug 2 in for I, we get 2/5 times 2 is 4/5, and 4/5 minus 2/5 is 2/5, so that gives us our second length. And of course, if we plug in a 3, we get 6/5 minus 2/5, which gives us 4/5, and that will continue on to 6/5 and 8/5, because when we plug a 5, we're going to get 10/5 minus 2/5, which is certainly 8/5. So this here seems to be the right formula. And once again, using the calculator, we could simply type into our sum 1 to 5, and if you prefer, the 2/5 is just a constant, so we could always pull the 2/5 out front. Now the crucial part is this is f of 2/5 I minus 2/5, so we need to remember to take and plug all of this into the original function. So all of this is going to be substituted in for the x. So we would have minus, and all of this goes in for the x, which would be 2/5 I minus 2/5, and what was our function? It was x squared, so all of this is squared. Okay, so it's minus all of that squared, and we still have the plus 5. So here's what you would need to type into your calculator and perform the sum from I equals 1 to 5. And do not forget to multiply by the 2/5. And here again, you should get something very close to 8.08 as we did over here. Okay, so now here we have concluded two examples dealing with your upper sums and lower sums. So here we have an example of upper sums where the rectangles are above the graph. And our previous example, we have an example of finding your lower sums where the rectangles went below the graph. Now I want to reemphasize that lower sums simply means your rectangles are going to be below. Just because we use the right endpoints here does not mean you're always going to be using the right endpoints for lower sums. Just as with the second example, where we were looking at our upper sums, that doesn't mean that you're going to always use the left endpoints. Sometimes you may use the right endpoints if you're looking for the upper sum if the graph is curved the other direction. This is called upper sums because your rectangles are going above the graph. For example, if your graph looked something like this, instead of your graph curving down, let's say that your graph was curved more upwards like this, and if we were to draw our upper sum, well, notice now if I go up to this point and over, up and over, whoops, too far, up and over, notice now this would be calculating our upper sum, but notice we're using the right endpoints instead of the left. So that means for this one, you wouldn't start at 0. So it all depends on the curve of your graph, whether you're going to use the left or right endpoints. But because here, if we were to use the right endpoints, we would be calculating the upper sums. If we were to use the left endpoints, then we would be calculating the lower sum. For example, if I started here and we went up, then our rectangle would look like this. So then we would go up to here and over. So here we would be using the left endpoints. So the left endpoints on this graph would be calculating the lower sums, because here in red your rectangles are below. So once again, the area of your upper sums, your rectangles go above, lower sums, your rectangles are below, and the actual area is somewhere in between.